Welcome back to the Deep Dive. We're so glad you're here with us.
It's great to be back.
Today, we are looking at a figure who, honestly, he sort of defies the usual boxes we like to put historical figures in.
He really does.
You usually have your science guys over here, your Newtons, your Galileos, your Einsteins, and then in a completely different building, sometimes on a different planet, you have your philosophers, your theologians.
Yeah, your Kierkegaards, your Augustines.
Exactly. And they don't usually talk to each other. They operate in different worlds.
Well, Stephen Jay Gould had that phrase, non-overlapping magisteria. That's how it's supposed to work. But today's subject, he didn't just overlap them, he smashed them together.
We are talking about Blaise Pascal.
Blaise Pascal. And the sheer scope of his life is just staggering when you think about it.
A man who lived only 39 years. I mean, that's the first thing that hits you. Born in 1623, gone by 1662.
A very short window.
And in that brief window, he managed to live what feels like 3 or 4 completely distinct, brilliant lives. He invents the mechanical calculator when he's basically still a teenager.
To help his dad with his taxes, no less?
Right. Then he lays the groundwork for probability theory.
Yeah.
All because a gambler friend asked him a question about a game.
A very practical problem.
And he revolutionizes physics by proving that the atmosphere, the air around us, actually has weight.
Yeah.
And then, after all that, he just pivots.
Yeah.
He abandoned science to become one of the most profound, most challenging religious writers in the entire Western canon.
It is a dizzying resume. I mean, it really is. And the thing that makes Pascal so compelling, so fascinating to dive into, is that he isn't just a jack of all trades.
Oh, yeah.
He was a master of all of them. He didn't just dabble. When he decided to do math, he fundamentally changed mathematics. When he turned to physics, he broke a 2,000-year-old Aristotelian consensus. And when he finally turned his mind to God, he wrote this collection of fragments, the Pensées, that philosophers and theologians are still fiercely arguing about 400 years later.
So the mission for this deep dive, then, is to try and figure out how all those pieces fit together. Because on the surface, the person who invents a calculating machine seems like a completely different person from the guy who secretly sews a prayer into the lining of his coat.
It seems like a contradiction.
It does, but I have a feeling you're going to tell me they're actually the same person driven by the same thing.
They absolutely are. I think the common thread, the engine driving him through all these different fields, was this relentless, almost desperate pursuit of certainty, of truth. Whether he was looking for truth in the precise meshing of gears in a machine, or in the empty space of a glass tube, or in the, silent contemplation of a monastery, he was applying the same rigorous, uncompromising, analytical intellect. He just wanted to know what was real.
Let's start at the beginning then, because the origin story here feels absolutely vital to understanding the man. Blaise Pascal, born in Clermont-Ferrand, France.
June 19, 1623.
His mother passes away when he's just a toddler, only 3 years old. So he's raised almost entirely by his father, Etienne Pascal.
And Etienne is a fascinating, crucial character in his own right. He wasn't just some bureaucrat. He was a tax collector, yes, but he was also a member of the noblesse de robe, which was the administrative nobility.
So an educated man. A powerful man.
Very. And an amateur mathematician himself. He was very well connected in the intellectual circles of Paris at the time. When Blaise was about 8 years old, Etienne actually moves the family, that's Blaise and his 2 sisters, Gilberte and Jacqueline, to Paris.
And he makes this really interesting decision to homeschool them, which, I mean, in the 17th century, that's not exactly the norm.
Not at all. But Etienne had a very specific, very rigid curriculum in mind. And the most famous part of that curriculum was what it was missing: mathematics. He had this idea, this pedagogical theory, that a child's mind should be trained first on languages and the humanities, Latin, Greek. He thought mathematics was too compelling, too absorbing, maybe even too taxing for a young mind.
He thought it would be a distraction.
Total distraction. So he literally banned geometry from the house. He hid the textbooks. He told Blaise flat out, you are not to think about mathematics until you are at least 15.
Which, I mean, if you know anything about raising a curious child, that is the single worst tactic you could possibly employ.
It's a colossal tactical error. You tell a brilliant kid that something is forbidden.
It becomes the only thing they want. The most interesting thing in the world.
Precisely. It became the forbidden fruit. So Blaise starts asking questions. What is geometry? What does it even do? And his father gives him this very vague, general answer. Something like, oh, it's the study of how to make precise figures and find the relationships between their parts.
And that was all he needed.
That was enough. The fuse was lit. And this leads directly to what might be the most famous story about Pascal's childhood, the kitchen floor incident.
Right, he's 12 years old at this point.
About 12, yes. And Etienne comes home one day to find his son on the floor with a piece of charcoal drawing on the tiles.
Just doodling, he probably thought.
At first, maybe, but he watches for a bit. And he sees Blaise's drawing shapes, circles, triangles, lines. But here's the thing. Because no one had ever taught him the official words, he was making up his own language for it.
Oh, that's incredible.
He called a circle a round. He called a line a bar. He was building his own private lexicon for geometry.
So he's not just drawing.
He's doing so much more. Etienne realizes that Blaise isn't just making pictures, he's constructing proofs. He is, from first principles, working his way through Euclidean geometry.
Without a textbook, without a teacher.
Completely on his own. By the time his father found him, he had, allegedly, and this is according to his sister Gilbert's account, he had independently rediscovered and proven the first 32 propositions of Euclid's elements.
Okay, let's just pause on that for a second. The 32nd proposition of Euclid is the one that says the sum of the angles in a triangle equals 2 right angles.
Yes.
180 degrees.
Yes.
He derived that from scratch using charcoal on a tile floor at 12 years old.
That is the story that has come down to us. Now, modern historians might debate whether he reconstructed the entire sequence perfectly or if he was just grasping the core logic of it. But either way, the intellectual achievement is it's staggering.
It's off the charts.
He deduced the axioms of geometry alone in a room. And when Etienne realized what was happening, that his son had effectively reinvented 2,000 years of Greek mathematics in their living room, the story goes that he wept.
He must have realized he couldn't stop it.
He knew. He gave up. He went and got Blaise a copy of Euclid's Elements, and Blaise, of course, just devoured it in a matter of days.
And that just opened the floodgates. Because it wasn't long after that, I mean, he's still a teenager, that he's not just learning math anymore. He's contributing to it.
At 16, he writes the essay on conics.
On conic sections.
Which is a short but incredibly dense treatise on conic sections. Ellipses, parabolas, hyperbolas, all the shapes you get by slicing through a cone.
And inside this essay, he presents something new, what we now call Pascal's theorem.
Or the mystic hexagram, which is a much better name.
It is a great name. Explain that to us. What is the mystic hexagram?
Okay, so it's a foundational concept in a field called projective geometry. Imagine you have any conic section, let's just say an oval to make it easy. Now you draw a hexagon inside it so that all 6 of its corners, or vertices, are touching the edge of the oval.
The hexagon can be all skewed and irregular, right?
Totally irregular, doesn't matter.
Fine.
Now take the opposite sides of that hexagon and extend them out like lines until they cross each other. You'll get 3 intersection points. Pascal proved that those 3 points will always lie on a single straight line.
No matter how you draw the hexagon.
No matter how you draw it, it feels like magic when you see it drawn out. It's this hidden order. And it's important to remember, this was cutting-edge stuff. This wasn't just solving old problems. This was creating new mathematics. He sent his paper to Father Marin Mersenne in Paris.
Who was like the central node of the European scientific internet at the time.
He was the guy. He connected everyone. And Mersenne, of course, shows it to the biggest name in the game, René Descartes.
The I think, therefore I am guy. The philosophical heavyweight. And you'd think he'd be blown away by this, but he wasn't.
He was skeptical. In fact, he was worse than skeptical. He was dismissive. When Mersenne showed him the essay, Descartes' first reaction was, I do not believe a 16-year-old wrote this.
You thought the father wrote it.
He assumed it was Etienne, the father, trying to, pass off his own work to build up the family name. He just couldn't accept that this level of mature, abstract reasoning could come from a boy.
That's sort of the ultimate backhanded compliment, isn't it? This is too good to be yours.
It really is. And even after he was finally convinced that, yes, the kid actually wrote it, Descartes was still sniffy about it. He said something along the lines of, well, I can see how a boy might stumble onto this one little proof, but he won't go much further with it.
Wow.
It just shows you I think, the tension between the established, rigid, Cartesian way of thinking and this intuitive, almost frightening brilliance of Pascal.
So by 16, he's already a mathematical prodigy. He's gotten the attention and the scorn of the most famous philosopher in Europe. But then real life sort of intrudes. His father, Etienne, gets a new government post.
Right, this is a crucial shift in the story. Etienne had briefly fallen out of favor with the powerful Cardinal Richelieu, but he gets reinstated and is sent to Rouen in Normandy to be the king's tax commissioner.
And Rouen at this time was a mess.
A total mess. There had been tax revolts, the city was in chaos, and Etienne's job was to go through years of disorganized records and figure out who owed what. He had to assess and collect taxes from thousands of people, and the sheer volume of the arithmetic was crushing.
You have to picture the scene, right? Night after night, the father is just hunched over a desk, buried in ledgers, surrounded by flickering candlelight, doing endless columns of addition and subtraction by hand.
And Blaise, who's now about 19, sees his father just suffering under this mountain of labor, and he decides he's going to help. But he doesn't just offer to, double-check the slims.
No. He thinks, I can build a machine to do this for him.
I will mechanize this mental drudgery.
This is the birth of the Pascaline, the mechanical calculator. And I think we often just gloss over this. We say he built a calculator, but we really need to understand what an engineering nightmare this must have been in the 1640s.
It was a nightmare. Because this isn't a simple machine that just adds 1 plus 1.
Right, because of the money system.
Exactly. France wasn't using a nice, clean decimal system. They were using livre, sol, and denier.
Walk us through how that works. It's confusing.
Okay, so a livre was the main unit, sort of like a dollar or a pound. But there were 20 sols in a single livre. And then there were 12 deniers in a single sol.
So it's base 12, then base 20, then base 10 for the rest.
Exactly. So if you're building a machine to add this up, you can't just have every gear have 10 teeth. You need a gear with 12 teeth for the deniers, which then has to turn a gear with 20 teeth for the sols, which then has to turn the livre gears.
And they all have to work in perfect sync.
In sync. And the real killer, the problem that had stumped everyone before, was the carry mechanism.
You mean like when you're adding and you get to 9, you add a 0 and carry the 1?
Precisely. On the machine, if your sol's wheel is at 19 and you add 1 more sol, that wheel has to click over to 0, and it has to give a push to the next wheel, the lever wheel, to move it forward by 1.
So it's a chain reaction.
It is.
Yeah.
And if you have a number like 9,999 lever and you add 1, you have to carry across 4 or 5 heavy brass gears all at once. The cumulative friction, the force required, would jam any simple machine. It would just lock up.
It's like a domino effect of friction and force. So how did he solve it?
He invented a mechanism of pure genius. It's called the sautoir. It's basically a little gravity-assisted pawl, like a tiny weighted lever. As you turn a number wheel, it slowly lifts this little weight.
Okay.
Then, right when the wheel clicks past its final number, say from 11 to 0 on the denier's wheel, that little weighted lever drops. And the energy from that falling weight provides the kick, the little burst of force, needed to turn the next wheel 1 notch.
So he's isolating the force.
He's isolating it. He's using gravity as a tiny temporary battery for each individual carry. It meant the user felt the same easy resistance whether they were adding 1 to 1 or 1 to 9,999.
That is just so clever. But it must have been incredibly difficult to actually build.
Oh, it was a torment. The metalworking skills in the 1640s, they just weren't up to the kind of precision that Pascal needed. He went through more than 50 prototypes. He had to personally stand over the blacksmiths and the clockmakers because they kept getting the tolerances wrong.
He spends 3 years on this, right? He finally gets a working model in 1645. He even gets a royal patent from the king. This should have been a world-changing invention.
And technologically it was. It was the first truly functional calculator that could be operated by a non-expert. It worked. But as a business,
A disaster.
a complete and total disaster, a commercial failure.
Why? I don't get that. If it saved so much time and effort, why didn't every accountant and merchant in France buy one?
2 main reasons. First, the cost. It was outrageously, exorbitantly expensive. The fine materials, the precision labor. A single Pascaline cost more than most skilled craftsmen earned in a lifetime.
So it becomes a status symbol.
Exactly. It became a toy for the aristocracy. If you were a wealthy duke, you'd have a Pascaline on your desk to show off his cleverness to your friends, but you probably weren't using it to actually do your estate accounts.
It's the original expensive tech gadget that nobody really needed, but everyone wanted on their desk.
It absolutely is. And there was also, interestingly, some resistance from the clerks and accountants themselves, a bit of fear of, job replacement. They worried this machine would make them obsolete.
The first fears of automation.
You could say that. In the end, only about 20 finished machines were ever built over a decade. But the legacy, of course, is massive. Pascal proved that mental labor calculation could be mechanized. He's really one of the grandfathers of computer hardware.
So he's conquered theoretical math. He's basically invented hardware engineering. Now let's pivot to the next big phase of his life. We're in the late 1640s now. The family has moved back to Paris. And Pascal gets fascinated by physics, specifically the physics of nothing.
The physics of the void. This was one of the hottest, most contentious scientific debates of the entire 17th century, the nature of the vacuum.
And the prevailing wisdom, going all the way back to Aristotle, was horror vacuum.
Nature abhors a vacuum.
We hear that phrase a lot, but what did that actually mean to them? Was it just a poetic way of speaking?
No, they took it absolutely literally. Aristotle and his followers, which included Descartes, by the way, believed that space is a plenum. It is completely full. There are no empty gaps. If you move an object, air, or some other invisible matter, an ether instantly, magically rushes in to fill the space.
So for them, a true void, true nothingness, was physically impossible.
And maybe even theologically impossible, because if God is omnipresent, how can there be a place where nothing, not even God, exists? So asserting that nothing could exist was a deeply controversial, even dangerous idea.
But then Pascal hears about these strange experiments being done down in Italy.
By Evangelista Torricelli, who was a student of Galileo. Torricelli had taken a long glass tube, sealed at one end, filled it completely with mercury, plugged the open end with his finger, and then flipped it upside down into a bowl of mercury.
And when he took his finger away,
the column of mercury in the tube fell, but it didn't fall all the way. It stopped at a certain height, about 30 inches, or 760 millimeters.
Leaving a gap at the top of the tube in the sealed end.
Exactly, the Torricellian space. And the big question was, what is in that space? The Aristotelians scrambled for explanations. They said it must be filled with mercury vapor, or a pocket of that invisible ether. Pascal heard about this and had a simpler idea.
He said, no, it's empty. It's a vacuum.
It's nothing. And being Pascal, he didn't just write a polite paper about it. He designed a show. He loved these big, dramatic, public demonstrations.
He was a bit of a showman.
A total showman. He published a paper called New Experiments with the Vacuum in 1647. And he repeated Torricelli's experiment, but he did these wild variations. He used water and red wine instead of mercury.
I love the detail about the wine.
Right. He used different liquids to prove it was about density and weight. And because water and wine are much lighter than mercury, the column stood much, much higher. He had to use glass tubes that were 40 feet long and strap them to the masts of ships in the middle of a courtyard in Rouen. It was a spectacle.
But the crucial part was his explanation for why the liquid stood up in the tube at all.
Yes. The old guard, the Aristotelians, said that the vacuum at the top was actively pulling the liquid up, a kind of suction force. Pascal suspected the exact opposite. He thought it was the immense weight of the ocean of air above us, pushing down on the surface of the liquid in the bowl that was forcing it up into the tube.
Atmospheric pressure. The idea that we are all living at the bottom of a deep sea of air.
That's the concept. And to prove that, he came up with a brilliant idea for an experiment. He realized that if air has weight, then there must be less air and therefore less pressure at the top of a mountain than there is at the bottom.
This is the Puy de Dôme experiment.
This is the definitive mic drop moment of 17th century physics. Pascal reasoned it all out, but there was a problem. He was always sickly. He suffered from debilitating stomach pains, terrible migraines his whole life. There was no way he could hike up a mountain himself.
So he outsources the work.
He does. He writes a letter to his brother-in-law, Florent Perrier, who conveniently lived near the Puy de Dôme, which is a large volcanic mountain in central France.
I can just imagine the letter. Dearest Florent, hope you are well. Would you mind doing me a small favor in climbing a nearly 5,000-foot mountain while carrying a very delicate glass tube full of toxic mercury? Thanks, Blaise.
That's pretty much it. And to his credit, Florent did it. On September 19, 1648, Perrier assembled a team of local dignitaries, priests, officials, doctors, to act as official witnesses.
He wanted to make sure it was all documented properly.
Oh, yes. This was science as a legal proceeding. So first, they set up the barometer in the garden of the Minim Fathers Monastery at the base of the mountain. They measured the height of the mercury column. It stood at 26 French inches and 3.5 lines.
And then they start climbing.
Then Perrier and his team start the 3,000-foot ascent to the summit. When they get to the top, in the wind, they set up the apparatus again.
And the result?
The mercury had dropped. It was significantly lower. It was now only 23 inches and 2 lines, a difference of more than 3 inches.
Which is a huge difference.
It's massive. And to be thorough, they measured it at several points on the way back down, and the mercury column rose steadily and predictably as they descended, returning to its original height back in the garden. It was irrefutable.
The weight of the air was the cause. The suction of the vacuum was a myth.
It was dead. And Pascal, to confirm it, replicated the experiment himself on a smaller scale at the top of a church bell tower in Paris. This changed everything. It wasn't just about how barometers work. It fundamentally changed our understanding of the world we live in. We aren't in some magical full plenum. We are on a rock, wrapped in a finite blanket of gas that obeys physical laws.
And this seems to have cemented his idea of what science should be. He established a really rigid standard.
He did. In a famous letter to a critic, a Jesuit named Etienne Noel, Pascal basically laid out the modern principle of falsifiability 100 years before Karl Popper. He said, in effect, your theory can explain 99 phenomena perfectly, but if one single repeatable fact contradicts it, your theory is false. Period.
It doesn't matter what Aristotle said.
Yeah. It doesn't matter what authority says. All that matters is what the mercury does in the tube. It was a revolution in method.
So we have the calculator. We have atmospheric pressure in the vacuum. Now we're moving into the early 1650s. His father dies in 1651. Pascal is now independently wealthy. He's a bachelor living in Paris. And this is what scholars call his worldly period.
It is. Now, we shouldn't overstate it. He wasn't some great debauched libertine. But he definitely enjoyed the finer things in life for a while. He had a coach and 4 horses, he frequented the fashionable salons, and he fell in with a very specific crowd, writers, aristocrats, and gamblers.
And professional gamblers, by their very nature, are obsessed with odds and fairness.
They have to be. One of Pascal's friends was a writer and a man about town named the Chevalier de Marais. He was a very keen gambler. And de Marais came to Pascal with a question that had apparently stumped mathematicians for centuries. It's famously known as the problem of points.
Okay, what's the scenario here?
The setup is simple. Imagine you and I are playing a game of chance, say, flipping a coin. We've each put 50 gold coins into a pot. The first person to win 5 rounds gets the whole 100-coin pot.
Got it.
But for some reason, we have to stop the game early. The candles burn out, the police raid the gambling den, whatever. And when we stop, the score is, you have won 4 rounds, and I have only won 3 rounds.
So I'm ahead.
You're ahead. The question is, how do we divide the 100 coins in the pot in a way that is perfectly mathematically fair?
Well, the simple answer is just to give it all to me since I was winning. Or maybe split it based on the ratio of our scores, so a 4-to-3 split.
Right, those are the intuitive answers. But de Marais and Pascal knew that neither of those is truly fair, because the fair way to divide the stakes must depend on the probability of what would have happened if the game had continued.
So you're not looking at the past, at the scores we already have. You're modeling the future.
That is the crucial revolutionary leap. They are trying to quantify the future. So Pascal, intrigued by this, starts a correspondence with another one of the great minds of the era, Pierre de Fermat.
Who was another one of these brilliant amateurs. He was a lawyer by trade.
A lawyer in Toulouse. And in a series of letters back and forth in the summer of 1654, these two men, Pascal and Fermat, solved it. They realized you have to map out all the possible future outcomes.
So in our game, if we play one more round,
there's a 50% chance you win and the game is over. You take the pot, and there's a 50% chance that I win, in which case the score becomes tied 4-4. Then we'd have to play a final deciding round. By mapping out this tree of possibilities and weighing each branch by its probability, they calculated what they called the expected value for each player.
And this is it. This is the birth of modern probability theory.
This is the moment. Before this, the future was seen as the domain of God or fate or just pure blind luck. It was fundamentally unknowable. Pascal and Fermat proved that while you can't predict the specific outcome of a single future event, you can absolutely predict the pattern of outcomes over the long run. You can tame uncertainty.
This underpins, everything in our modern world. Insurance markets, stock market analysis, medical trials, election polling, quantum mechanics.
It all starts right here, with 2 French guys trying to figure out the fair way to split a gambling pot.
And in the middle of all this work, Pascal decides to synthesize a lot of his thinking about numbers into his treatise on the arithmetical triangle.
Right. What we all learn in school as Pascal's triangle.
That pyramid of numbers we've all seen, where each number is the sum of the 2 numbers directly above it.
Now, to be clear, he didn't invent the triangle itself. The pattern was known to mathematicians in China, Persia, and India for centuries before him, but Pascal was the first person to really explore all of its properties systematically and write them down.
And he showed how it connected to probability.
He did. He showed that the numbers in the rows are the binomial coefficients. So if you want to know, say, how many different ways can you choose a committee of 3 people from a group of 5, you just go to the 5th row of the triangle and the 3rd number in, and there's your answer. It's a beautiful, elegant tool.
There's one more little mathematical story from this period involving a toothache, the cycloid.
Yes, though this happens a bit later, in 1658, after his major religious conversion. But it shows his mind was still working on these problems. He was suffering from a terrible, raging toothache that kept him awake all night. And just as a way to distract himself from the pain...
A very Pascal thing to do.
Very. He started thinking about a famous unsolved problem in geometry, the cycloid. That's the curve traced by a point on the rim of a rolling wheel.
He used geometry as a painkiller.
And it worked. As he got deeper into the problem, the pain vanished. And he took this as a divine signal, a sign from God that it was okay for him to engage in mathematics as long as it wasn't for vanity.
So he solves it.
He solves it in 8 days. He figures out the area under the curve, the volume of the shape it creates when rotated problems that had stumped giants like Galileo and Torricelli. And then, in a very strange move, he held a contest under a pseudonym, challenging the other great mathematicians of Europe to solve it.
And then he declared himself the winner of his own contest.
It did. It was a little controversial. Great minds like Christopher Wren and John Wallis submitted solutions, but Pascal, writing as Amos d'Ettonville, judged his own anonymous solution to be the only fully correct one.
It just shows that even as he was becoming more religious, he still had that incredibly sharp, competitive, almost arrogant edge to him.
Absolutely. But that competitive edge was about to be redirected toward a very, very different kind of opponent. We have to talk about the Great Shift, the event that changed his life forever, the Night of Fire.
Because for all his worldly success, all the fame from his math and physics, Pascal was deeply unhappy.
He described it as a period of profound spiritual dryness, even disgust. He had the money, he had the fame, he was celebrated in the salons, but he felt this deep sense of his own wretchedness. And at the same time, his younger sister Jacqueline, whom he was very close to, had become a nun at the Port Royal Abbey.
And Port Royal was the absolute center of a controversial religious movement called Jansenism.
We really need to define Jansenism because it is the essential backdrop for the entire second half of Pascal's life.
So what was it?
You can think of Jansenism as a very rigorous, very austere, reformist wing within the Catholic Church. They were heavily influenced by the writings of St. Augustine. They believed that human nature was totally and utterly corrupted after the fall of man in the Garden of Eden.
So we're inherently broken.
Utterly broken. We are incapable of doing any good on our own. We can only be saved by God's grace, and that grace is irresistible, but it is given only to a select few. The elect. You can't earn it. You can't work your way to heaven.
It sounds a lot like Calvinism, but inside the Catholic Church.
It is very, very similar in its theology to Calvinist predestination. And that, as you can imagine, got them into a huge amount of trouble with the mainstream church, especially with the Pope and the powerful Jesuit order. But for Pascal, this rigorous, all-or-nothing, uncompromising view of the world, it resonated with his personality. He was a man of absolutes.
So this is all swirling in his mind. And then we come to the night of November 23, 1654. Pascal is 31 years old.
He's at his home in Paris. It's late at night. And from about 10:30 p.m. to 12:30 a.m. for 2 solid hours, he undergoes some kind of intense, direct, mystical experience.
We don't really know what happened.
We don't. He never spoke about the details to anyone verbally, but we know he grabbed a piece of parchment and in a frantic, ecstatic state, he scrawled down a series of short, fiery phrases to capture the moment.
And this is the document that we now call the memorial.
Yes, and it starts with the single word fire written in huge capital letters at the top, and then it says, God of Abraham, God of Isaac, God of Jacob, not of the philosophers and the scholars.
Wow. Not of the philosophers and the scholars. That is a direct rejection of his entire life up to that point.
Yeah.
He's saying the abstract geometric God of Descartes, the prime mover, that's not the real God.
Not at all. He goes on, he writes, certitude, certitude, feeling, joy, peace, and then joy, 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 tears of joy. This wasn't an intellectual conclusion. This was a visceral, emotional, overwhelming encounter with a personal deity.
And what he did with this piece of paper is, to me, the most telling part of the whole story. He didn't frame it on his wall.
No. He folded it up and he sewed it into the lining of his coat, right over his heart. And for the rest of his life, whenever he got a new coat, he would carefully unpick the seam, take out the precious parchment, and sew it into the new one. He literally kept that fire close to his heart every single day. A servant only discovered it by chance after he died.
That moment really marks the death of Pascal the scientist and the birth of Pascal the religious apologist. He effectively retires from math and science and goes to live in seclusion at Port Royal.
And almost immediately, he gets drafted into a war, a theological war. The Jansenists were under fierce attack from the Jesuits. The Sorbonne in Paris was trying to formally censure a leading Jansenist theologian, Antoine Arnauld. The Jansenists were losing the public relations battle. They needed a champion. They needed someone who could write.
So they cap the new guy, they tap Pascal, and he produces the Provincial Letters.
Which are 18 letters written under the brilliant pseudonym Louis de Montelt, supposedly a simple man from Paris writing to his friend back in the provinces. And they are an absolute masterpiece of satire and polemic.
And he's attacking the Jesuit method of moral reasoning, which he calls casuistry.
Casuistry. It sounds like casual, but it's much more complex. Casuistry is case-based ethical reasoning. The Jesuits developed it as a way to help people navigate complex moral situations in confession.
So on the surface, it sounds helpful.
It can be. But Pascal argued viciously and brilliantly that the Jesuits were abusing it. They were using hyper-complex, hair-splitting logic to create loopholes that could justify almost any sin. He accused them of being slimy moral lawyers who could get you off the hook for murder or theft if you just defined your intention in the right way.
Can you give us an example of the kind of Jesuitical logic he was mocking?
Oh, absolutely. He has a field day with it. He mocks the idea that while killing someone in a formal duel is a mortal sin, you can get around it by, say, simply going for a walk in a field where you happen to know your enemy is waiting, and then if he attacks you, well, you can kill him in self-defense.
It's all about plausible deniability.
Exactly. And he just shreds this kind of tortured logic. But the genius of the letters is that he does it with humor. They are genuinely funny, they're witty, they're conversational, they're not dense theological tracts.
And this is where we get that famous quote about brevity, isn't it?
It is. In the 16th letter, he apologizes to his correspondent, writing, "I have made this longer than usual because I have not had time to make it shorter." And that captures his style, perfectly lucid, precise, devastatingly efficient.
And these letters became a sensation. They were illegal, but they were passed around secretly.
A black market bestseller. The king tried to ban them and have them burned, but everybody in Paris, from the intellectuals to the shopkeepers, was reading them. They completely changed French prose. Before Pascal, serious French writing was often flowery and dense. Pascal wrote with the clarity of a geometric proof, but the wit of a stand-up comedian. Later giants like Voltaire and Rousseau both pointed to the Provincial Letters as the birth of modern French prose.
So he successfully defends his friends, he publicly humiliates the Jesuits, but he has a much bigger, more ambitious project in mind. He wants to write a full, comprehensive defense of the Christian religion. An apology.
This is the great unfinished work of his life. And it's what eventually became the book we know today as the Pensées, which just means thoughts. He never finished it. He died, leaving behind just hundreds of notes and fragments, some meticulously organized and tied into bundles with string, others just random phrases jotted on scraps of paper.
So later editors had to piece it all together like a puzzle.
Exactly. Which is why it can be a challenging read. But even as fragments, they are just devastatingly powerful. He focuses so intently on the contradictions of the human condition. He does. He paints this terrifying picture of humanity suspended between two infinities, two abysses. On one side, you have the abyss of the infinitely large, the silent, terrifying universe of stars and galaxies that is too big for us to comprehend. And on the other, the abyss of the infinitely small, the world of mites and atoms that we can't see. We're trapped in the middle, he says, unable to grasp either extreme.
Which leads to his most famous metaphor for humanity, the thinking reed.
Man is only a reed, the weakest in nature, but he is a thinking reed. It's such a perfect image. He fully acknowledges our physical fragility. A vapor, a drop of water, the universe doesn't have to arm itself to crush us. It's easy.
Right.
But our dignity, our greatness lies entirely in our thought. We know that we are dying. We know the universe is crushing us. The universe, he says, knows nothing of this. That consciousness, that awareness of our own wretchedness is what elevates us.
And it's from this analysis of the human condition, the state of being lost, confused, and self-aware, that he produces the most famous and certainly the most controversial part of the Pensées.
The wager.
It's Pascal's wager, yes. Yeah. And it's so often misunderstood. People think it's supposed to be a logical proof of God's existence. It's not.
He didn't think you could prove God with reason.
He explicitly believed you couldn't. He thought the distance between our finite minds and an infinite God was, well, infinite. Reason is powerless. So he reframes the question. This is not a logic problem, it's a decision problem. A gamble.
He brings the gambler from his worldly period back into his theology. He absolutely does. He imagines he's talking to a skeptic, a friend from the salons, who says, I just don't know if God exists or not, so I'm not going to choose. I will suspend judgment. I won't bet.
Which seems like a reasonable position.
It does. But Pascal's brilliant move is to say, you can't suspend judgment. You have no choice. You are already embarked. You are alive. Your life is moving forward toward death. You are already in the game. You must place a bet.
So he draws up the betting matrix. Let's walk through the 4 quadrants of the wager.
Okay. Quadrant 1. You choose to bet that God exists, and it turns out you're right. He does exist. What's the result?
Infinite gain, eternal happiness, heaven.
Okay. Quadrant 2. You bet God exists, and it turns out you're wrong. He doesn't. What did you lose?
A finite loss. You lived a virtuous life. Maybe you missed out on some parties or pleasures. Then you died, and that was it. You lost a few earthly experiences.
Right. A limited, finite loss. Now, the other side. Quadrant 3. You bet that God does not exist, and you're wrong. He does exist.
Infinite loss. Damnation. Losing out on everything that mattered.
The ultimate bad outcome. And finally, quadrant 4. You bet God doesn't exist, and you're right.
A finite gain. You enjoyed those parties you otherwise would have missed. You died, and that was it.
So when you lay it out like that, it becomes a problem of probability and expected value, just like the problem of points. You have a choice between a finite risk for a potentially infinite reward on one side and a finite reward for a potentially infinite risk on the other.
And Pascal's conclusion is that no rational gambler, no sane person, would ever bet against the infinite. Even if you think the probability of God existing is tiny, 1 in a billion, the potential infinite payoff still makes it the only rational bet.
The expected value of believing is always infinite. That's the cold, hard logic of it.
But people, and I include myself here, people have always had a problem with this argument. It feels cold. It feels cynical, mercenary.
It feels transactional. I'll believe just in case to cover my bet.
Right, and it feels like you're just faking it. You can't just decide to believe something because it's a good bet.
And Pascal, brilliant psychologist that he was, anticipated this objection completely. He has his skeptics say, okay, I'm convinced by the logic, but I can't make myself believe. What do I do? And Pascal's advice is chillingly practical. He says, if you want to believe but can't, you must cure yourself of your passions, which are the obstacle. Start acting as if you believe.
Go through the motions.
Yes. Go to Mass. Take the holy water. Mumble the prayers. He calls it abhors, which literally means to stupefy yourself or to make yourself like a beast, like the unthinking faithful peasants. He argues that by taming your skeptical intellect through habit and ritual, genuine faith might eventually follow.
It's fake it till you make it, applied to the salvation of your soul.
It's a profound psychological insight. He understood, perhaps better than anyone, that belief isn't always a purely intellectual switch you can flip. It's a habit of the heart, and habits are formed through action.
So we are nearing the end of his short life now. He is racked with illness. He's pouring his soul into these fragmented thoughts. But he has one last surprising invention left in him. In 1662, the very year he dies, he decides to fix the traffic problem in Paris.
It's just the most wonderful and unexpected final act. The carrosses à 5 sols, the 5 sol carriages. Pascal looked at the city of Paris and he saw a problem of logistics and social equity. If you were poor, you walked everywhere. If you were rich, you had a private carriage. There was no middle ground.
So he invents the public bus system.
He basically does. He, along with some powerful friends like the Duke of Rohannes, formed a company. They got a royal patent. He designed a system of large multi-passenger carriages that would run on fixed rides across Paris for a fixed price of 5 sols.
But the truly revolutionary part, the part that makes it modern, was the schedule.
That was the genius of it. The carriages left at specific regular times, regardless of whether they were full or empty.
Which is the single defining feature of true public transit, reliability. You know the bus will be there.
It was an instant success. The first line opened in March of 1662. There were crowds in the streets cheering for it. It was a sensation. Pascal had even stipulated in the plans that the profits should go to the poor and that the poor must be allowed to ride.
It just goes to show that his mind never ever turned off. Whether it was the abstract geometry of a hexagon or the practical logistics of moving people across a city, he saw systems and he wanted to optimize them.
But he didn't live to see his bus line flourish. By the summer of 1662, his health had completely collapsed. He was in constant agony.
Do we know what was actually wrong with him, physically?
It's very difficult to diagnose retrospectively from 400 years away, but the consensus is that it was likely a combination of stomach cancer and malignant tuberculosis. He had terrible stomach ulcers. The autopsy that was performed revealed grave damage to his stomach, his liver, and they even found lesions on his brain.
And yet, in those agonizing final months, his religious asceticism became even more extreme.
It did. He sold his fine furniture and his carriage to give the money to the poor. He had moved into his sister's house, but he begged her to let him be taken to a hospital for the incurables so that he could die among the poorest of the poor.
A request his family denied?
They refused. He was simply too sick and unstable to be moved. He spent his final days in and out of consciousness, suffering from terrible convulsions and pain. He made his last confession, he received communion, and his last recorded words were, "May God never abandon me." He died on August 19, 1662.
Gone at 39.
39.
The legacy he leaves behind is, well, it's fragmented, just like his Pensées. It's everywhere. We use the Pascal as the SI unit of pressure. There's a major programming language named Pascal.
Computer chip architectures are named after him. And we use his probability theory every single time we check a weather forecast or read a political poll. And we use his arguments or argue against them every time we debate the existence of God.
And in a deeper sense, we still struggle with the same core problems he did. We're all still thinking reeds, aware of our own mortality, often terrified by the silent, infinite spaces of the universe, distracting ourselves with our own modern versions of gambling and bus schedules.
That's the enduring power of Pascal. He seems to have seen the modern condition, our condition, before modernity had even properly begun. He saw that science would give us immense power, but it wouldn't and couldn't give us peace.
I think I want to end with that famous thought of his. He wrote, "All of humanity's problems stem from man's inability to sit quietly in a room alone."
Divertissement. Distraction, the constant need to be doing something, to be entertained, so that we don't have to face the big questions, to face ourselves.
So a final thought for all of you listening.
Yeah.
Maybe after this is over, just for a few minutes, turn everything off, sit in a room, be quiet, and see what happens.
It might be the hardest experiment Pascal ever proposed.
Thank you for joining us for this deep dive. We'll see you next time.